finished up density, this was our model. We had solids, right? They were tightly compact together. They were kind of forming, not necessarily to the container. They weren't touching, but pretty close. This was our liquid, which had some more space to it. They were more fluid. They're going to make the shape of the container. And then we have our gas, which is super spread out. And also forms to any container. It doesn't have a defined shape. It doesn't even have a defined volume. This has a defined volume. This has a defined volume and shape. So those are kind of what our differences are just on a physical level when we look at these things. Like density, we talked about how density is the amount of particles within a given area. So each one of these things are related to 1 cubic centimeter of space. But then we did a lab. We did a lab where we updated this model. So now we're going to be talking about our new model, which has energy involved. So in here, I'm going to put these little lines. So these little lines, we lovingly refer to these as whooshies or wigglies. Either are fine in my case. And what they're showing is energy. Because even in a solid, there's still energy in here. So things are still slightly moving around. If you remember back to the video that we watched in class, they're doing the dance, right? They're coming together, pulling apart, coming together, pulling apart, coming together, pulling apart, and they're dancing. So liquids then, which have more space and more movement, they have a little bit more energy. So I'm going to give these 2 wigglies as opposed to my previous one where some of these are sharing a wiggly, some of them are only have 1. So I'm going to give these 2. And excuse my artistic detail here. I'm not the best artist in the world. So if this has 1 and this has 2, and we have a gas. Gas is sometimes represented as 3, so there's 2 different ways that you can do this. One is that you can put like 3. I like to put even 4 because it's showing a huge gain in energy. Another way that you can show gas, I'll show you one over here, is using these lines because it also shows a little bit of direction. It shows that it's moving very fast, that the wigglies are barely hanging on, which I like either. So if you use either of those things, it's totally fine in class. So we saw the pinwheel. That was one of the things that we saw. And I'm showing this is less energy and this is more energy. So as I'm heating up the center here, the energy ended up traveling at different rates down some of these different prongs. So this one right here, there was a lot of energy at the end, so the wax melted. Up here, same thing. Lots of energy at the end, the wax melted. That was my giveaway. That's how I knew the energy got to the end. And then these ones, these 2, the wax did not melt. And no melting here because the energy didn't travel down yet. This one has barely any travel. This one has a little toward the end here, but nothing at the end. So not enough energy to melt that wax because we know that in order for something to change state, it needs energy. And something I like to put out is that if you show me a dot like this, what you're saying is there's no energy, which means that we're at absolute 0. We're going to talk exactly about what absolute 0 is later this year. But let's look at a different model. The ball and ring. So what's different between these 2? This was slightly bigger. It did not fit through the ring. This was smaller, fit through the ring easily. Well, this one had more energy, and that increase in energy caused those particles to space out. Now, what I want to notice here is this is a before, this is an after of the same object. So how many particles should I have? Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we have to consider conservation of mass, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then we have to have the same amount of dots on either side. So really for today, our big takeaway is that our model has been updated. Our model's been updated to show that energy is causing these particles to either be closer together or further apart. More energy further apart, less energy closer. So we should start to kind of think about, how might you model water condensing on my windshield? How might you model an ice cube melting? What does the energy look like in those diagrams? And we're going to practice some of that this week. More coming up. Talk to you guys soon.